Welcome to the first module for KIN 331 Personal and Community Health. This course is going to focus a lot on the topic of epidemiology, which of course I will explain here shortly what that is. But what I wanted to do today is introduce this idea of epidemiology and the basic statistics that go along with it. The first few lectures will be pretty statistics heavy, math heavy. So we'll do a lot of review and make sure that you understand that before we go forward in understanding how all of this applies to exercise and physical activity, which is really why we're interested in this topic and why this is part of your curriculum. So welcome to the course, and I hope that you will enjoy it and find it beneficial. So to start, what is epidemiology? Well, epidemiology broadly is the study of the distribution and determinants of health-related states or events in specific populations. So it has to do with health, and the two key words, of course, here are underlined: distribution and determinants. So distribution really refers to who has the disease or the health-related state that we're interested in. So maybe you're talking about cancer. So what is the distribution of lung cancer, for instance? Does it vary by state? Does it vary by country? Does the type of person that gets lung cancer vary? That is an idea of the distribution. Determinants would be what causes it. So, of course, you're probably all aware that if we're talking about lung cancer, one risk factor that is associated with lung cancer is cigarette smoking. So that would be a determinant of lung cancer. And then there's a third step, really, after we define who or study who has the disease and what causes it. The next question, really, and the last step of the epidemiologic chain of events is, what do we do about that? So if we think about this in terms of physical activity, which is really the reason you're in this course, who is physically active? What causes them to be physically active, or what predicts physical activity is another way to think about it. And then once we know who's physically active and what predicts who's going to be engaged in physical activity, what do we do about it? How do we change that? Really, how do we get more people to be active? And so this is the type of progression of thinking that we're going to go through. We're first going to describe who, then talk about what or determinants, and then what's the next step. So this is an example of distribution, or who has a disease. You've probably seen a map like this before. This is the 2010 obesity map put out by the CDC, the Centers for Disease Control. And what this is showing is within the United States, what is the distribution of obesity? So you can see on the bottom of the figure, there's the legend. So this yellowish color suggests or shows which states have 20 to 24% of the population within that state who is classified as obese, meaning they have a BMI greater than 30. The orange color means that within those states, 25 to 29% of the population is obese, and then the red states, greater than 30% is obese. This is just an example of classic epidemiology. What is the distribution of obesity in the United States? This map shows us that. So the next step again was determinants, what causes disease. So this is another way of saying what is a risk factor. So if we want to know what causes lung cancer, we would study risk factors for lung cancer, and of course we know that smoking is one of those. You could take any condition, health-related, and identify risk factors. So maybe you want to study what causes premature birth, or what causes ingrown toenails. It could be anything. But all of these diseases or outcomes have risk factors. Some diseases or conditions we know what causes them, and others the risk factors are still unknown. So a risk factor is defined as a characteristic that is, if present, increases the probability of disease. So again, for instance, smoking is a risk factor for lung cancer. If you smoke, that doesn't guarantee that you will develop lung cancer. Not everyone who smokes gets lung cancer. Some people who get lung cancer don't smoke, but it is a risk factor. Epidemiology was really, this field came about in the mid-1800s. John Snow was a scientist living in London. He only lived a pretty short while, as you can see from he was born in 1813 and died in 1858. But he is known for studying a significant cholera outbreak in London in the mid-1800s. And back then, the theory was that cholera was caused by what they called bad air. And as you're probably aware, that's not a thing. And it really was kind of a superstition about what caused cholera. Nobody knew. John Snow decided that he thought the cause was contamination of the water source. The reason he thought this was that he noticed a high density of cholera in people who lived near this certain well at that time. Water came from wells, and so you would go to the closest well to you geographically for your source of water. So a lot of people near this one particular well developed cholera. And there was a prison nearby that well. And nobody from the prison, or very few people in the prison, got cholera. But Snow noticed that the prison had its own well, separate from this other. Also geographically nearby, there was a brewery. None of the workers there at the brewery, there were a large number of employees, none of them developed cholera. But Snow realized those workers only drank beer, not water. So the fermentation process would take care of the contaminants. So based on these three observations, John Snow hypothesized that the source of cholera was. And this is a map of a neighborhood in London where the center part, the darkest gray, is the highest incidence of cholera. So lots and lots of cases. And as you get further out from that well, the number of people that had cholera decreased. And so this is classic epidemiology, outbreak epidemiology. A lot of times people will think of epidemiology as the study of the outbreak of disease. And that's really originally what it was. And today, this field can be more relevant to chronic disease, heart disease, cancer, diabetes, and therefore, in terms of physical activity, we're interested in epidemiology as well. But this is how this field really came about. And again, John Snow is considered to be the father of epidemiology. So what he did was he described the distribution of cholera. That's what you saw in that map. Near the well, high number of cases of cholera. As you get further and further away from that well, fewer cases. He used that map, that distribution, to analyze all of these situations, the brewery, the prison, and he identified a risk factor that he thought was associated with the risk of developing cholera, and that was drinking certain water. And of course, the end goal of the reason we study epidemiology is to ultimately prevent disease. So If we know that cholera comes from contaminated water, now we can develop methods to treat water to prevent cholera. If you don't know what causes the disease, it's very, very difficult, if not impossible, to prevent it. And so identifying the cause must come before we can prevent or modify disease risk. So, who cares? How does physical activity fit into this? Well, in terms of studying the distribution, we can study physical activity levels across populations. Who is being physically active and who is not? We can, of course, study the relationship between physical activity and disease, various diseases. Does physical activity relate to cancer? Does it relate to obesity? Does it relate to diabetes? And so on and so forth. And then we can study how to get people to be physically active so that they do not develop the diseases that we know are related to physical activity. So again, that first bullet point is really the distribution. The second bullet point, the determinants. Is physical activity a determinant of any particular diseases? And then what do we do about it is that final step. So this is really the process we're going to go through this semester. We're going to spend the first several weeks really just looking at classic epidemiology, how to think like an epidemiologist, how to answer these questions, what kind of data are we going to see in numbers, and then we'll get more specific into how does physical activity relate to certain diseases later on in the semester. Okay, so now let's get started with some basic statistics in epidemiology. The reason I am presenting this information to you is because it's necessary for you to understand these statistics in order to interpret any epidemiologic literature that we're going to be looking at later to study how physical activity is related to disease. So first, let's start by defining some important terms. We have ratios, proportions, and rates. And so these are very similar and yet different, and the differences are important. So let's start with a ratio. A ratio is just a quotient of two numbers. So if you remember back to elementary school, quotient means division, right? So for example, 60 miles per hour. You travel 60 miles divided by 1 hour, that is a ratio. Anytime you have a fraction, that's a ratio. Ratio is a very general term. If there's a top and a bottom, a numerator, that's the top number, a denominator, the bottom number. If it's a fraction, it's a ratio. A proportion is a little bit different. A proportion is always a ratio because a proportion is also a fraction, but it's a specific type of fraction. So this is a fraction in which the numerator is contained in the denominator. For instance, 40% of residents own their own home. Well, 40%, or 40 would be the numerator, and then 100 would be the denominator, because that's residents who either own their home or don't own their home. So 40 own their own home, 100 own or don't own. So the numerator is contained in the denominator. A proportion always ranges between 0 and 1, or it can be a percentage on a scale of 0 to 100%, and a ratio. A rate is another type of ratio, but this is a specific type of ratio that involves a quantity, a change. Almost always, in terms of epidemiology, the denominator is time. So, a change in time. So the denominator involves some time. Miles per hour would be, yes, it's a ratio, but it's also a rate. Here's an example. There are 9,000 new lung cases per year. That's an absolute rate. It's simply the number of new cases. but it's a time component per year. There's also something called a relative rate. So the example there would be 9,000 new lung cases per 100,000 people per year. So that gives 9,000 new lung cases relative to some other number. With the absolute rate, 9,000 new lung cases per year, we don't know if you mean in the whole world, in this state, in a certain university. We have no idea. So if you give it in terms of something else, for example, per 100,000 people per year, that's a relative rate. Okay, so let's do a practice. The number of children born prematurely in the state of Alabama in 2015 divided by the number of children born in Alabama in 2015. Is this a rate, a proportion, or a ratio? I'm going to give you a minute to think about it. And of course, this is an online course, so I'm not going to be able to ask you, but it's to your benefit to stop this recording, write down what you think, and explain why you think it. The answer is proportion. The reason is that the numerator is contained in the denominator. It's not a ratio because there's no time piece to this. Yes, it says in 2015, but it's not per year or per minute or per hour or any of that thing. So proportion, because the number of children born prematurely in the state in a certain year divided by the number of children born in the state, not the denominator does not include those born prematurely. But those born prematurely, they were all born. So they're the number that's on the top, say it's 500. There are 500 children born prematurely in Alabama in 2015. And there are 10,000 born in the state. So that would be 500 divided by 10,000. But that 500, they're part of the 10,000. All of those children that were born prematurely, they were still born. So they're included in the denominator. I hope that. A couple more important terms are incidence and prevalence. Incidence is defined as the number of new cases of disease in the population during the period, a certain period of interest. So new cases is very important. So for instance, how many people get flu in a certain time of the year? Maybe in December, which is a time of year that it's more common to get flu than maybe July. Incidence is more appropriate for acute conditions. Acute means something that comes and goes. It doesn't last. So the flu, for instance. You get the flu, eventually you get over the flu, and then you don't have the flu anymore. Whereas something like multiple sclerosis is not an acute condition, that's a chronic condition. So number of new cases, incidence, that's appropriate for acute conditions. On the other hand, we have a term called prevalence. This is the number of persons in the population who have a certain disease at any given point in time. So this is more appropriate for chronic conditions, so because it includes incidence and duration. Yes, the number of people who get MS, but they have it for a long time, typically many, many years. And so prevalence is better for giving us an idea about how common conditions are that last a long time. Maybe certain cancers, any variety of long-lasting chronic diseases. So here is a handy little table that I think does a good job of describing the difference between prevalence and incidence. Again, prevalence is the number of people that have a condition at a given point in time. Incidence is new cases. So think of incidence as the number of events developing the flu. Think of prevalence as entities having MS over a long period of time. With the source population prevalence, think of it as at risk to be a case. Once you get MS, you are a case of MS. Whereas with the flu, you're at risk to become a case. You become versus be. Again, one implies long-term, the other implies short-term. Static versus dynamic. And the uses, the use of incidence is typically to discover what causes something. That's etiologic research. So we may want to know what's causing the flu. Where are we spreading the flu? Maybe at Samford, the flu is being spread in the dorms. And so if we know the number of new cases in students who are living in the dorms versus students who aren't living in the dorms, we may realize, I think it's coming from the dorms. Whereas prevalence, it can be used to plan treatment, preventative measures, and so forth. We can also report things in rates, incidence rates, and prevalence rates. These are typically expressed as a percentage of the population. So remember, the rate has a time component. So for instance, the number of cases divided by the average population size. So an incidence rate for flu for students living in the Samford dorms. Here's an example. The number of cases is 126. So 126 students develop the flu. 953 live in the dorms. So that, if you take 126 and divide it by 953, the incidence rate is 13.22%. This means that 13.22% of students living in the Samford dorms contracted the flu, developed flu, during the study period. Maybe it was a month, we don't know. It doesn't say, but however long the study went on. So that's an incidence rate. The prevalence rate, we would never calculate a prevalence rate for flu because flu is acute. So something chronic like colon cancer, a prevalence rate would be appropriate. So the prevalence rate for colon cancer in people living in Birmingham, let's say that 1,257 people in Birmingham, which has a population of 937,385, have colon cancer. So what you do is calculate it the same way as the incidence rate. You take 1,257 divided by the population of Birmingham, and we can calculate that 0.0013% of Birmingham residents have colon cancer, or you can also express it per 1,000 residents, and in that case it would be 1.3 per 1,000 Birmingham residents. So again, the incidence rate and the prevalence rate are calculated the same way. They just indicate chronic versus acute conditions. Sometimes the population that's at risk of developing a disease can vary over time. In that case, it's more appropriate to calculate something called cumulative incidence. Say, for instance, you get the flu, but within a season, once you get the flu, you're not at risk of it anymore. So really, during the rest of flu season, you're not at risk. And if a lot of students are getting the flu, the number of students at risk of flu actually goes down throughout the course of the flu season. We need to account for that to get a true estimate of the risk of developing the flu in the Samford dorms. So then we would calculate what's called the cumulative incidence. This is essentially when the denominator changes. The number of people at risk of flu or whatever is changing. We do this because it gets at a more accurate picture of the true risk of developing flu. So here's a different example. Hand, foot, and mouth disease is a common childhood illness. It's not pleasant, but it's a virus, okay? So say there's a breakout of this condition, this virus, at preschool A. In October, 12 children get hand, foot, and mouth. 75 children go to this preschool, attend this preschool. So, 12 out of 75, 16% is the incidence rate in October. In November, 8 more children get the disease. So the incidence rate is now 20 out of 75 because we had 12 in October and 8 in November. So 26.7% of the students at preschool A have developed hand, foot, and mouth. But that's not really the true risk of developing hand, foot, and mouth in November at this preschool. 26.7% sounds really high. The true risk of developing hand, foot, and mouth goes down actually because once you get hand, foot, and mouth, you don't get it again. So we need to subtract this number 12, the number in October. They're not at risk anymore. So it's really 8, number of children in November who get the disease, divided by an altered denominator, a denominator that would be 75 minus 12. And if you do that math, you come out to 12.7%. So the risk of getting hand, foot, and mouth at preschool A in November was actually 12.7%, not 26.7%, because we accounted for children who were no longer at risk. What about December? Well, to know how many children, or to know the risk, we would need an accurate denominator, and it would be 55 in this case. 75 minus the 12 who got it in October and minus the 8 who got it in November. Again, this is done to estimate a more accurate true risk of developing a disease. Okay, another measure of incidence that we can use is called incidence density. This is done to account for time exposed. So some conditions, your risk depends on how long you're exposed to whatever risk factor. So with cumulative incidence, that was on the previous slide, remember, that was the number of new cases divided the number of people at risk. Incidence density is different because it's the number of new cases divided by what we're going to call population time. This is not the number of people at risk, but it's a variable that accounts for how long they were exposed. For instance, say that you work at a factory where you were exposed to asbestos. That's a chemical that's been associated with lung cancer and some very dangerous health outcomes. If you worked at this factory for 50 years, your risk of asbestos is probably higher than somebody who worked at the factory for 1 year. That's what incidence density does. It accounts for exposure time, and it's very important in certain situations. If we go back to the hand, foot, and mouth example, what if 3 children enrolled in preschool A in November? They have been exposed for a different amount of time than the children who were exposed originally, and that. So when we think about disease, here's a question for you that will help you measure whether you're understanding these principles. Does high prevalence indicate high risk? If a disease is very, very common, does that mean that you're at high risk of developing that condition? The answer actually is not necessarily, and I want you to think about why that might be. In what scenario would high prevalence not indicate high risk? It can, but it doesn't always. This is because some conditions are almost always survived. So what it means is that, yes, prevalence is high, but it doesn't always mean that individuals who don't have the condition are going to develop it. So let's give an example. Birmingham, Alabama, let's say this city has a high prevalence of coronary heart disease, disease of the coronary arteries of the heart. That doesn't necessarily mean that people in Birmingham are at higher risk than people who live in, say, Boston. What if Birmingham, if 10% of the population has coronary heart disease, and in Boston, 4% has coronary heart disease? Does that mean that living in Birmingham puts you at higher risk than living in Boston? Not necessarily. We can't say that for sure. The reason is that perhaps people come to Birmingham because the best treatment in the country is available here. That's one scenario that might cause people with coronary heart disease to come to Birmingham. You cannot always assume that high prevalence indicates high risk. Also, another scenario would be maybe Birmingham has better treatment of coronary heart disease, and so people tend to survive this condition, and people in Boston die from it because the treatment isn't good. Both of those scenarios suggest or explain why this might be the case. The prevalence rate can increase due to survival. So people have coronary heart disease, but they're living longer. They don't die from it, but incidence stays the same. So again, the point is that you can have a high prevalence rate. That doesn't necessarily mean that the incidence rate is high as well. Okay, so I want to give you an example of cumulative incidence and incidence density. This is from a paper, a research paper that was published, really two different research papers. There was one study, both of these studies were about breast cancer rates, okay? One study called the Nurses Cohort Study, it went on for many, many years. It's actually still ongoing, and they studied nurses. And so they studied these women, they were all females, for many, many years over time, and they found the breast cancer rates in this group, this cohort, to be 6.7 cases of breast cancer per 1,000 women. There's another study called the NHANES cohort. We'll learn more about that later. Right now, just know that it's a different group of people. But they found breast cancer rates in that group to be 18.2 per 1,000. Well, if you just look at these numbers, what would you think? Boy, it seems like nurses are less likely to get breast cancer, or something along those lines. Those are pretty different. The NHANES group was 3 times more likely to develop breast cancer. So these calculations, 6.7 per 1,000 and 18.2 per 1,000, those are cumulative incidence. Okay? However, in the nurses study, what you don't see is the number of years of follow-up. So, in the nurses study, there was a 4-year follow-up. If you calculate the incidence density, which you don't really need to know how to do that mathematically, that's not the point. But if you calculate the incidence density where you account for exposure time, you come out to 1.68 cases per 1,000 women years. So women, the number of years women were exposed, not just the number of women exposed. If you do the same calculation for the NHANES study, which had a 10-year follow-up, you come out to 1.68 per 1,000 women years. So if you calculate the incidence density, the risk is exactly identical in the nurses study and the NHANES study. But if you look at the confidence interval, the cumulative incidence, the rates look really, really different. So what does that mean? Who cares? The moral of the story is it's very dangerous to compare cumulative incidence when the follow-up years were different. One study had 4 years of follow-up, one study had 10 years. You have to account for that. So I want you to be aware of this later on as we start to read research. Here's another important point to think about as you are reading studies that have looked at risk of disease. Say a physician tells you, anecdotally, I've seen 100 runners in the past year with IT band syndrome. It's iliotibial band syndrome. This is a painful condition of inflammation of the IT band. Does that mean that runners are at high risk of IT band syndrome? Hopefully your immediate answer was, we can't tell. It depends. It depends on how many runners the physician has seen. It depends on the denominator. This example in the bullet point on the left gives us a numerator, 100 runners. But we don't know 100 runners out of how many. If the physician has seen 150 runners in the past year and 100 of them have IT band syndrome, then yes, that sounds like really, really high risk for runners. 100 over 150 is 68%. That's a very high risk of developing IT band syndrome. If the physician has seen 10,000 runners and 100 of them have IT band syndrome, then the incidence is 0.1%. The point is, you have to know the denominator. That's very, very, very critical when estimating risk of a certain condition. Alright, now let's kind of switch gears and talk about types of rates. When we look at disease and study disease, determinants and distribution of disease, you're going to see a lot of rates. Remember, rates have a time component. It's a fraction with a time component. There are 3 different types of rates that I want to talk about. Crude rates, specific rates, and standardized rates. Crude rates are what they sound like. They are crude. It is just how many people have the condition. It does not account for characteristics like age, race, gender, none of that. The problem with crude rates is if the population is unique in any way, or if you're comparing two unlike populations, like maybe you're comparing men and women, the crude rates can be misleading. For instance, you can't compare rates of breast cancer in a population that's mostly female compared to one that is mostly male. If you compared rates of breast cancer amongst nurses to the general population, that would be misleading. Likely you would see that the nurses have a higher crude rate of breast cancer because there's a higher percentage of female nurses than the percentage of females in the general population. And so that would be misleading. So what we do is we use standardization. When we talk about mortality rates, age is obviously very important. Older people are more likely to die of anything because age is such a risk factor for mortality. And so it's very important to account for age when looking at mortality rates. So this is from your textbook, and this is an example of crude death rates, So this is just showing that in this hypothetical population, the crude death rate, the number of people who died out of the number in the population, is 4.5%. And this other hypothetical population B, the crude death rate, 616 people died out of 20,000, so approximately 3%. So in population A, the crude death rate was higher. That's a crude rate. It's simply the number of people who died over the population, or the number of people who have cancer over the number in the population, or the number of people who have 6 toes over the number of people in the population, whatever. Sometimes it's necessary to account for an important characteristic in the population, depending on what you're studying. If you're studying mortality, it's important to account for age. If you're studying breast cancer, it's important to account for gender. If you're studying prostate cancer, it's important to account for gender, and so on. So this is the same exact table that you saw from the previous slide, and now I want to focus on the bottom. This is a calculation that used a technique called standardization. What they did is they standardized based on age. So it depends, the mortality rate depends on how many people are young versus old. And so again, I'm not so interested that you understand exactly how to do the math. I'm not going to focus on that here. But here, if you calculate a standardized death rate for population A, you get about 3%. Up here, same population, the crude death rate was 4.5%, the standardized death rate is 3%. In population B, the crude death rate was 3%, but the standardized one was 6%. So, again, these are the same exact groups, but when you look at the rates standardized, they look different. So now population B has twice as high of a death rate as population A when standardized, when taking into account the age of the population. So this is an example just showing that it's very important when studying mortality that you account for age. Okay, so here's another example. This is direct standardization. Say you want to know the death rate, how the death rate in Florida compares to the rest of the nation. Well, Florida is a popular destination for retirees, so the population tends to be older. So if we just looked at crude death rates for Florida versus Alabama, say, it might look like, oh my gosh, something terrible is happening in Florida. People are dying. Well, is that really true, or does it just happen that the population is older? That's really the question that we want to know the answer to. So Florida's crude mortality rate, looking at this data, so what this means is 30.3 or 30% of Florida's population is between 0 and 25, 28% is between 26 and 50, 22% is between 51 and 75, and 20% is 76 years or older. And these are the death rates for each of those age strata. Strata is a category. So 3 out of 1,000 for the youngest group, 6 out of 1,000, 12 out of 1,000, and then the oldest group, not surprisingly, has a higher death rate, 62 out of 1,000. So, Florida's crude mortality rate is these numbers, 3, 6, 12, 62, all added together, divided by 1,000. So 83 out of 1,000. If we want to standardize that, what we do is we multiply 0.3 times 3 and divide that by 1,000. So 0.9 divided by 1,000. 0.28 times 6 divided by 1,000, that's 1.68. 0.22 times 12 is 2.64. And 0.2 times 62. Then we add 0.9, 1.68, 2.64, and 12.4 together, and you come up with 17.62 per 1,000 is the standardized Florida mortality rate. So 83 versus 17.62. Those numbers are really different. It's very important that we standardize based on age. What this number means is 17.62 per 1,000. This is the death rate for Florida if Florida's population was like that of the rest of the United States. We know it's not, but we've standardized to the regular U.S. population. So this is the distribution of the U.S. population, not Florida, United States population, of the group that we are standardizing to. There's another technique called indirect standardization. Sometimes you don't know what the death rate is in Florida for each age group. So in that case, we would do a technique called indirect standardization. We want to calculate how many deaths we would expect in Florida if the rate was the same as that of the United States. So if we know the death rate for 0 to 25-year-olds in the U.S., we just don't know it for Florida. Specifically, we can do indirect standardization. So this is the population of Florida per 1,000. So 200, 220, 260, 320. Or you could present these in decimal form too. 20% of the population, 22%, 26%, 32%. So the largest group is the oldest group in Florida. And this is the death rate per age category in the U.S. Remember, we don't know the death rate for 0 to 25-year-olds in Florida. So to indirectly standardize, we took 200 times 3 divided by 1,000. That's the expected number of deaths. 220 times 6 is 1.32. 260 times 12, and so forth. And we added these numbers together. 0.6 plus 1.32 plus 3.12 plus 7.04. Add those together. 15.3 expected deaths per 1,000 people in Florida. This is the number of deaths you'd expect in Florida, 15.3, if the rates were the same as that of the United States population. Okay, so really, who cares? What if the actual number of deaths, this is the expected number, what if the number of deaths in Florida is actually 25 per 1,000? Well, we know that that's something not good is happening. Something about Florida specifically. Maybe all the alligators have gone crazy. Maybe the pollution is terrible. Maybe there was a terrible hurricane that killed a lot of people. Whatever, we would want to investigate what is happening in Florida if the actual number of deaths in Florida is greater than 15.3 per 1,000. This is a way to examine if there is some abnormality that we should investigate. Is there some disease or condition or something that could be prevented that is causing people? Okay, so here's a couple of ways to remember direct versus indirect. When you use the mortality rates of the population of interest, that was Florida in our example, you are directly standardizing. We knew the actual true mortality rates in Florida. When you use the mortality rates of the standard population, that was the United States in our example, you are indirectly standardizing. Again, just remember that standardization, it seems quite complicated, I know, but really what its purpose is to remove the effect of an unwanted variable. In our example, it was age, but we could remove the effect of any number of variables. In my field, I'm interested in exercise during pregnancy, so sometimes we want to remove the effect of the number of previous pregnancies. A woman may respond differently if she's had 3 babies than if she's had none. So that's an example. We could remove the effect of any number of variables, depending on what we're studying. And then direct standardization is used when stratum-specific rates are available. Stratum is just the category, the different ages. Indirect standardization is used when stratum-specific rates are not available. Just a word of caution, it's very good to standardize when necessary, but sometimes standardizing can hide some interesting differences. So it's important to look at not just standardized rates. Look at crude rates and specific rates also whenever possible. So that's going to conclude the new material for this week. Please make sure that you read the syllabus in detail. You will have gone over that in class. You need to make an introduction post, and the details are on Moodle and in your syllabus. This week, by Friday, you will need to take the Module 1 quiz. It's open for 1 hour, and so you'll need to allocate that much time to it. And then discussion number 1 is also posted. Again, if you need information on how to do these things, please see the syllabus. Also for due dates, see the syllabus. The due dates will be the same each week. If you have any questions, feel free to email me. My contact information, again, is in the syllabus, and I look forward to this semester.